Today's lecture 12. We're just going to do one lecture, not split it into two parts. Talk about distances and speed as we've done already. I'll also talk about position and velocity, which sounds like basically the same thing, but there are differences. I like to differentiate between speed versus velocity and say they are different things. And I think that is the best way to approach it. So even though the word velocity is sometimes used to mean speed, I want to treat them differently. They are, of course, related to each other. The derivative of a function at a point, we've defined that already. But I want to emphasize today that the derivative itself is also a function. That just like the original function, f of x, can be graphed. You can graph f prime of x as well. And we'll look at some examples as we go. But at the start here, I want to just talk about, well, testing, math classes, and life, first of all. And then I want to review some things. I want to talk about the applications in this course, remind you of what those applications are, and talk about what we've done so far and where we're going. And remind you of those visuals from the first lecture of the moving cars before we get back into the main content. First of all, it's natural to feel anxious during tests, okay? We had our test last week. I'm sure everybody felt anxious. Everybody does, including me. Okay, I always felt anxious during tests too. Okay, I'm not immune from it. I've done badly in math tests before. Okay, I'm not immune from doing badly on math tests. For me, it happened at a higher level in graduate school. When I was going for my PhD, I had really, really tough math tests that I had to take, and I failed a number of them. Okay, I was able to, in those cases, eventually pass to be able to get my doctorate in math. I've been teaching for about, well, at Bethel for 21 years and a couple other places before there. But I also, even just 15 or so years ago, decided to take a class at the university to learn more about actuarial science. And I understood the material fine, but I still had anxiety going into the test. Even then, okay? I was 30-some years old then, and I had anxiety. I was with a bunch of 20-year-olds or so in that class, and I had anxiety going into the test. I did fine, but I did have anxiety. The note cards are not meant to be there for you to spend time during the test searching for formulas. They're there just to comfort you and use only if absolutely necessary. Okay? You really should study well enough that you think going into the test you can do okay without the note cards. Okay? Because people who use the note cards too much, spend too much time with them, they rely on them too much instead of really thinking, and they tend to do worse on tests. So they're there really most just to reduce your anxiety. You should not rely on them. Tests are actually meant to be learning experiences. They're not just meant to cause anxiety. Okay? But you have to approach them in the right way. Partially, they're an inducement to study and synthesize what you have learned. But that does mean not cramming, right? Don't wait until the last night before the test. It means studying consistently, reviewing what you've learned consistently, which does mean you got to be organized with your time. Okay? You got to plan out your days, think about your days. What are priorities to get done first, then second, then third? But with math especially, you know, you need to include probably at least a half hour of study, whether it's working on problems or doing reading, pretty much every day, maybe even longer. Okay, not that you can't take breaks once in a while. They're also meant to be, when they are returned, something you can learn from. Learn from your mistakes, even if the grade is much worse than you're hoping for. Don't throw it away. I've heard people throwing their tests away. Okay, don't do that, even if it's a really bad grade for you. Look at them, think about them, study them, figure out what you did wrong and how you can improve. You can improve. That article that I mentioned on Moodle, I suggested that you read it. Sarah Seals' story, How I Discovered My Love of Math, is about a person who struggled with math when she was younger, and in fact she had teachers who said, well, you're just not very good at math, okay? But she kept persevering over many years and is now at the point where she's going for her doctorate in math. Actually, she contacted me first to alert me about this article. She came in contact with my YouTube channel and appreciated some things that I had on there for her, and she sent me a message, and she told me about this article that was written, and I think it's a pretty inspiring article. She kept at it over many years. She got better. Now, many of you will not have time to study math for many years. You have just maybe this semester or maybe a few years, but you can get better. That's the moral of the story, if you work at it hard enough, okay? While grades are important, they are still relatively far down in the list of most important things in life, okay? Yes, it's ideal to get good grades, to get better grades than you may be hoping for. That does lead to opening doors in your life, but it's not the most important thing in your life, okay? More important in this class in particular is that you do the best you can, that you learn as much as possible. And then you realize that your value as a person created in God's image is not dependent on your grades, okay? It doesn't depend on your grades as far as how God views you. It also doesn't depend on your grades on how I view you, okay? You are still valuable to me as a fellow believer in Christ. It's not dependent on the grades that you get. Meditate on Jesus' words in Matthew 6:26. Look at the birds of the air. They do not sow or reap or store away in barns. In other words, they're not sowing crops and reaping crops, and they don't have barns. Yet your heavenly Father feeds them. Are you not much more valuable than they? You are created in God's image. Okay? Doesn't depend on how you do on your math class or math test. Okay, so take that to the bank. It's not determining your value. All right, let's review the main applications that we study in this course, talk about what we've done so far and where we're going. Motion, we're going to talk about motion today. That's our main topic today. Distance traveled and speed, position and velocity, relationship to derivatives is the main topic. In motion, there's a subject called kinematics, which is just describing motion. Essentially, that's what we're doing so far. We're just describing motion with functions. We're not really fully understanding motion. That's dynamics. It's forces in Newton's second law. If you've had some physics, you know about that. F equals ma is the big equation there. We will talk about that in here, but just not yet. Okay. Maybe talk about it a little bit today, but mostly we're doing kinematics, just trying to describe motion, not fully understanding it yet. Flows include fluids, pollution, and traffic. We haven't really talked about that yet, except for that first day where I was showing you the visuals, for example, of the flow of those colored waters going into the vats. That will come up pretty soon here, maybe even a little on Wednesday. Certainly next week we'll talk about some flows as far as applications go. We have talked about exponential and logistic growth and exponential decay. For example, population growth and radioactive decay. We talked about population growth a fair amount, radioactive decay a little bit. That's where the idea of half-life came into play. Finance, I talked about compound interest in the context of those bonds, and I showed you the formula. It was on an old test. I haven't actually tested you on the compound interest formula. I might for the second exam. So that's something we will talk about from time to time as an application. Annuities, loans, and bonds. We talked a little bit about bonds. Probability and statistics, the foundation of data science. We've done a little bit of data modeling. Right? I've talked about, for example, the modeling of the daylight hours in Minneapolis in 2019 and how we try to use a sinusoidal function to match that data. It wasn't perfect because the residuals didn't follow. They followed a pattern instead of being random, but it did a pretty decent job. Okay? We'll do more kinds of data modeling as we go as well. Remember, there was one key equation. This is something we're really going to focus on today. Much of calculus consists of generalizations and extensions of one simple equation: distance equals rate times time. And its cousin, its relative, rate equals distance divided by time. Okay? Actually, this is what we focus on first here today, essentially, and some on Wednesday. To find the rate, how fast are you moving, take the distance you travel divided by the time that goes by. Technically speaking, as this stands, that's an average rate. Average speed. It would be your exact speed if you traveled at a constant speed, like setting the cruise control on your car. There you're traveling at a constant speed. You can find that constant speed if you know the distance to travel and you know the time that goes by, the time elapsed. The first equation really is more related to integrals, which is the other main subject of calculus besides derivatives. Here are our visuals. We've got the 3 cars moving at a constant rate, different rates, but constant rates, moving at rates 1, 2, and 3, units of distance per unit of time. So the scale on the axis there, those are units of distance. You know, literally speaking, these are about 1 inch, literally on the screen, 1 inch apart. And the time is going by, is that literal seconds? No, it looks like it's going too fast to be a literal second. Yeah, that's going too fast. I'd have to slow it down. But if you pretend it's literal seconds here, then the red car is traveling 1 inch per second, the blue car is traveling 2 inches per second, and the green car is traveling 3 inches per second. You have to give units to give a precise real-life meaning. And you should be able to graph what's going on here. You can graph the speed, for example, as a function of time. In this case, the speeds are constant. Say for the red car at, well, for the blue car, say at 2, right here, that would be in inches per second. Time is in seconds. That's a constant function, a constant speed. Notice this is not the graph of the distance traveled. The distance traveled, so what we usually have been starting with so far, distance in inches, time still in seconds. The distance traveled keeps going up. Since it's a constant speed, it's going up along a straight line. Focused on the blue car here again. The slope of that line would be the speed, 2 inches per second. Again, I'm using inches because that seems to be the literal scale on the screen. Okay? The speed is really the derivative of the distance traveled. It's giving you the constant slope. The output of this function is always 2. That function is a constant function too. This function is not constant, it's linear. This function has a formula, f of t equals 2t, aligned with the slope of 2 going through the origin. It's direct proportionality. Its derivative is this function, f prime of t equals 2. So it's here I'm kind of going backwards. I'm starting with the speed and saying what is the distance traveled. And so far, including today, after this point, we'll start with the distance traveled and figure out the speed. Going from here to here, upwards, is differentiation, finding derivatives. Going from here back down to here is called anti-differentiation, also integrating. It gets more complicated. Let's skip that slide there. If the rate is changing. Here the speed is not constant. Again, say we focus on the blue car. Starts out kind of fast, then it slows down, then it goes faster, then it slows down. The speed, maybe it's kind of like a sinusoid. For all the cars, but for the blue, this would be like centered on 2 or so. That would be the midline, the average speed. This would be the graph of the derivative. Sinusoid, in fact, since it's starting at its peak, you could maybe model it with the cosine function. Shift it up by 2 units. What would its distance traveled look like? Something like this. The formula is no longer correct. It's not going to be a straight line anymore. It's steep, large slope when the car moves fast, right at the beginning. It's going kind of fast. Then it's got a smaller slope in there when the car moves slower. Then it's got a larger slope in here when the car moves faster. Hard to tell whether it's moving fast right away. I mean, it sort of pauses at time 0. I was thinking it sort of looks like it moves fast right away once the time starts going. So if we pretend that's the case, then it starts out with a steep graph here. Then gets less steep, then gets steeper, then gets less steep. Okay? These concepts and thinking visually like this and relating them to graphs are fundamental to understanding what goes on in the course. Okay? You want to make sure you get this. It's not just about formulas. It's about conceptual thinking about ideas with graphs. And nice to have animated visuals like this. Can I clarify anything there? All right, let's get into new details here. How do we measure speed? This is the title of section 2.1, which you've already read before the test. So far we focused on examples with formulas, and this example does have a formula, but I'm going to start off with data. You could measure the distance traveled, for example, every second. And essentially, this is what cars do when they're telling you how fast you're going, though it's probably measuring the distance traveled more often than 1 second. It's keeping track somehow of how far the tire has rotated, maybe every 10th of a second or something. Maybe every 100th of a second. And if you can keep track of how far the tire has rotated, and you know the circumference of the tire by knowing its radius, that can tell you how far you've gone during a 10th of a second or a 100th of a second. And that information gets translated then into a speed. Here's some data. Now we use standard scientific notation here. Time is in seconds. F of t is in meters. The n here means meters. So the units for speed would be meters per second. Time goes by and we're measuring how far we've traveled. These numbers are how far we've traveled. Data about some unknown function. The function giving you your distance traveled at any given time t. From time 0 to time t. Here's a graph of just the data points. You know, this is typical kind of data you might be able to gather in such a situation. You can graph it. It's tempting now to want to connect the dots, right? Connect the dots. You could connect them with straight lines, and I actually will be doing that. Technically speaking, when I do that, those are not the actual curve itself, because in all likelihood, there's really a true curve for the distance traveled, whereas this is a bunch of straight line segments pieced together. Those would be secant lines of the underlying curve. Some underlying curve, probably looking about like this, but those would be secant lines for it. The curve itself gives you the true distance traveled as a function of time. The data points are points on that curve. The straight line segments that are just used to connect the dots are just a quick way to connect the dots and give you estimates for how far you've gone. They also are secant lines again, so their slopes will give you average speeds. We'd like to estimate instantaneous speeds. Speeds at any moment in time. What is my speedometer saying? Which is a little bit paradoxical, thinking back to the paradoxes of the first day. How can you measure your speed if no time is elapsed, right? Because speed is distance divided by time, but if time is 0, you can't divide by 0. It's a bit of a paradox. We are going to define instantaneous speed, however, with limits. It's a derivative. But we can estimate the instantaneous speeds with average speeds. We're effectively connecting them to the straight lines like I mentioned. And the slopes of the secants are the average speeds. Okay, so I have the data. Those are the points. I went ahead and connected them with straight lines. That's not the true graph of the true distance traveled. In all likelihood, very strange for the true distance traveled to have corners in the graph. In all likelihood, in real life, the true distance traveled would be not just continuous, but smooth. I can find the slopes of those line segments, though, and get average speeds. Average speed from t equals a to t equals b is the distance traveled change in s, I'm going to call it, divided by change in time. S is the variable that represents distance traveled. Ys, well, is just kind of a standard thing to use. Don't let S make you think it's the speed, though. We're going to reserve V for speed because V stands for velocity. And as I already mentioned, velocity and speed are actually not the same thing. So it gets confusing that way. When something's confusing, you got to hear your teacher who's saying, I know this is confusing. Here's how to avoid the confusion. Okay? S just means distance traveled here. It does not mean speed. In function notation, it's f of b minus f of a divided by b minus a. Right? Think about our typical picture. A is here and b is over here. This number is f of a. This number here is f of b. Draw a red triangle in the picture. That's the change in f, which I've drawn to be positive, so it's also a distance. The graph could go down, however, and then f of b minus f of a would be negative. We'll talk about cases like that today. And b minus a is the length of that leg of the triangle. Assuming b is bigger than a, b minus a will be positive. And the ratio is the slope, then, of the line connecting these 2 points, which is not the curve itself, but is this line here. That's the secant line. There are lots of secant lines, not just one of them, even though I said the secant line. I can pick a and b to be anything and find the slope of a secant line and average speed over some time. The steeper this is, the faster you are going on average. If the graph is real steep, that represents very rapid movement, okay? Very high speed. The slope of the secant line would be large. On the other hand, if the graph is relatively flat like that, not necessarily straight, but relatively shallow in slope, the slope of the secant will be close to 0. And that represents motion that's slow, a small speed. Continuing the data-based approach, we might try to get more accurate by letting the distance be measured every 0.1 seconds instead of every second. I'm not going to look at a data table for this one because it just is too big. But we can look at the graph. Here's a graph of the data. Same situation. I actually do have an underlying function in the background that I'm using here to generate these data. But in real life, you would just have the data. The concepts still apply. I can still connect these dots with straight line segments, and the slope of those line segments would be average speeds over smaller intervals of time. Okay, so I did connect those dots there. The red lines or arrows are supposed to point at the little line segments between the dots. And these dots there are not data points. That's just saying there's going to be more arrows to draw in between here that I did not draw. Probably, maybe I should have. It might have been a kind of pretty picture. Draw all the arrows. Maybe for fun, before class next time I will do that and draw all the arrows. The slopes of those things are the average speeds. over these various time intervals. Since you're doing so many of them, you've got a bunch of different slopes. We're really, in saying this, we're really estimating the derivative of this function at a bunch of points as a function, f prime of t. If I made a new graph where the output of the new function had values that are equal to these slopes, which start out close to 0, then get bigger and bigger, I would be graphing the derivative. The derivative itself can be thought of as a function. It's the main new conceptual control, besides the velocity. Question?
If you're taking the derivative of those slopes then, so the second derivative, does that find the constant acceleration?
If it is a constant acceleration, I would find that, yeah. In this case, this happens to be a quadratic, so there would be a constant acceleration, but not in general.
In general, there would not be a constant
Right.
acceleration. Okay.
And it would be, you might have been alluding to this, but I'm not sure. It would be the slopes of the derivative of this that would give you the graph of the second derivative. Say that again? I could graph these slopes. We will be doing this a lot on Wednesday, by the way. All of them as a function of time. Get a new graph that's not going to look so different than this. Actually, it'll be straight, though, because this is quadratic. Its derivative will be linear. And then even whether that derivative graph is linear or not, I could redo the process. I could make a bunch of secant lines, find their slopes, and make yet another new graph. That's going to be the second derivative of the original function, we say. And it will give you the acceleration. Yes, in this case, this function happens to be quadratic, so its derivative graph is going to be straight, linear. And so those little secant lines are actually going to be the actual line itself. And the second derivative will be a horizontal line, it turns out. The slopes of the derivative will be constant.
Is a function of distance always to the second power?
No. In many applications it is. Yes, that's true.
So
but not in general.
So like if you have a function that's not quadratic,
yep,
and you take the derivative of that, then the velocity is not.
Then the velocity will not be a linear function.
Okay.
Right. Yeah. It's typical examples like we're going to see here soon where it ends up being a quadratic. The most common example being free fall in gravity.
Yeah.
Right. Then we can take a functional approach. We can come up with a function that approximates the data and differentiate that function instead. That's going to be a more efficient approach, you might say. Now, this is a little bit backwards. So in generating these data, I started with the function and then I generated the data. In real life, more typically, you'd start with the data and you want to generate the function. And it may not always be a good idea to generate a function. It may not always be a good idea to come up with a formula. That's not necessarily always a good idea. Sometimes it is, sometimes it's not. In this case, the function happens to be this function, which is quadratic. That was the function I used. And we can now calculate its derivative with the limit idea. So we're about to do a limit calculation. Okay? It's going to be a little bit complicated. It's probably worth writing down even though it's on the slides. And it's worth you personally thinking about it in each step. First, there's the definition of the derivative. For an arbitrary time t equals a. And I am going to do it at an arbitrary time, t equals a. I could do it at a specific time. That's a little easier. But you should be able to handle arbitrary times. That is an important skill to get out of this class, is being able to handle arbitrary times. So a is an arbitrary number. Could be 1, could be 2, could be 3.7, could be pi even. Any number a. This is the definition of the derivative, right? There's your difference quotient. It represents the slope of a secant line. Coming back to this picture over here. H is this distance right there. Sometimes we call that delta x. In fact, most of them called it delta x until last Monday and Wednesday. This then, if that distance is h, well, that means b minus a is h. And f of b minus f of a can be written as f of a plus h minus f of a. Because b equals a plus h. Right? Look at the picture. H is the distance between a and b, but it also says that a plus h will get you to the b. All I did there was replace the b by a plus h. It works down the bottom too, by the way. If you replace b by a plus h there, you get a plus h minus a, and then the a is canceled, leaving you with just an h. That's the definition of the derivative. Remember, for the second exam here, I am going to want you to be able to give reasons for each of these steps. This first equality, well, essentially this is just a description, definition in the sense the instantaneous speed at a, at time a, is defined to be f prime of a. That's just the definition of what instantaneous speed means. This is the definition of the derivative. What's the next step? Use the formula as the next step. Substitution into the formula. There I did. Yikes. Oh, and it didn't translate from a Mac to PC. Well, there are lines missing here. These are fractions. Right? Because the function is 1/4 t squared plus 1/2 t. So when I see an f of a plus h, I need to take the entire expression a plus h and plug it into the function and place it in the t. Fundamental to understand that, okay? And again, I know from past experience teaching this course, plenty of people don't understand that. So you see a 1/4, oops, fraction here too. You see a 1/4 t squared, t is a plus h. And then plus 1/2 t, t is a plus h. Minus f of a, that's f of a. Subtract the whole thing, so use parentheses around it. But then we can distribute the minus sign through. But if you make mistakes here, then you're going to run into trouble. Probably the fraction symbols continue to be missing here, so I'm going to continue on the board. Next step is just simplify. Expand out the a plus h quantity squared. Use FOIL, F-O-I-L. First, outside, inside, last. A plus h times a plus h. You'll get a squared plus 2ah plus h squared. Multiplying the 1/4 through gives you this. Right there. Hey, the fraction showed up. Well, not good. These things all show up correctly on my computer. That's, this thing right here is 1/4 a plus h squared, expanded out. Algebra skills are important here. This thing right here, that is the same as the 1/2 a plus h. It's again called the distributive property. And then again, I distributed the minus sign through. Really, I distributed plus -1 through the -1 through the parentheses. That's what I really did to get minus signs here and here. Continuing to simplify, stuff cancels, yay! That cancels with this cancels with that. We're so happy when that happens. If it doesn't happen, you're like, oh, I made a mistake somewhere. You probably did if it doesn't happen. Because now all the terms that are left involve an h in the top, and so an h can be factored out and divided out with the h in the bottom. Back to the screen here. Like that. I effectively did a couple steps on the screen going from here to here. I canceled the 1/2 a squared and I canceled the 1/2 a's. And I also factored out an h from what's left. This is one of the terms that's left right here. It's got a factor of h. When I factor the h out of that, I'm left with 1/2 a, like you see right there. This term did not cancel. It's got a factor of h. Factoring an h from that one gives you h times 1/4 h. You have the 1/4 h right there. And this one right here also has a factor of h and it did not cancel. Factor the h out of that one, you're left with the 1/2. can be checked going back the other way by distributing the h through. Sort of uncanceling the other term if you want. So again, definition of instantaneous speed, definition of the derivative, plugging into the function, you could call it substitution, simplifying. This next step is simplifying, but it's also something else. What else allows me to say this besides just simplifying? This is the most important thing, one of the two most important things for me. I should say three most important, sorry. Definition of the derivative is one of the three most important steps. The other two important steps are this one and the one that follows. What's the reason for this one besides just simplifying? We did divide out the h's, but what else? This is something I really emphasized. We didn't have to do. Yep, I want to ultimately plug in h equals 0. That's true. But why can I say this limit equals that limit? That's what I'm after.
Divide it out.
That's true, but I need something else.
Does the limit apply to everything in the parentheses and stuff?
It will, but I'm after something else. What did I really emphasize about graphs of rational functions, for example, after canceling common factors? The graphs should have holes in them. The graph of this thing as a function of h. Think of a as fixed, like 2. Think of this as a function of h. I could graph that as a function of h. It's undefined at h equals 0. But because it cancels something to something continuous at h equals 0, the graph of it as a function of h would have a hole in it at h equals 0. The limit would still exist. It's not a jump discontinuity. It's not an asymptote. It's a hole. It's a point missing. The limit still exists and equals the limit of this function because these two functions are the exact same thing when h is not 0. So the limits are going to be the same when h approaches 0. This last thing here is important, a really important reason as well. That's the continuity of this function at h equals 0. The simple graph function. Continuity says that even though the definition of the limit, it doesn't matter what happens at h equals 0, this function's special. It's continuous. It has all its holes, so to speak, filled in. There are no holes. Probably a better way to say that. We can evaluate the limit just by substitution. H equals 0 and give this. So that's continuity of this function of h. Think of a as fixed. By the way, whether a symbol like an a or an h is a constant or a variable is all in your head, okay? And you look at a bunch of equations and you're like, well, what's constant, what's a variable? It's all in your head. It's all in how you're thinking about it. I'm pretending a is some fixed number like 2 or 3 or 4. Here I'm thinking of h as the variable. I could graph this thing as a function of h. And this, again, is continuous at h equals 0, so I can plug in h equals 0 to find the limit. We're not going to, and that's not the last time I'm saying that stuff, okay? But make sure you think about it. How do we measure velocity? I said velocity is different than speed. How do we measure it? Well, we can still take a database approach if we wanted to. But for sake of time, let's quickly move on to the functional approach in a particular situation. And here's the situation of free fall. Right? An object that you've dropped, or you've thrown it straight down at the ground, or you throw it straight up in the air. Technically, also throwing it sideways like you would in most sports is a free fall as well, but it adds the extra complication of another dimension. We're trying to avoid that for the moment at least. So I'm only thinking about up-down motion here. Under the influence of gravity, assuming no or negligible air resistance. Negligible means it's so small you might as well just ignore it. Like when if I drop this, I will not drop it, it might break. But if I drop this, there's negligible air resistance for a short time at least. The equation I'm going to show you would be a very good model for that. It would not be such a good model for a feather. Okay? Feather, because of large air resistance compared to its mass, essentially falls at a constant rate. Things like rocks and presenters don't fall at constant rates. They speed up as you go down. There's an acceleration. Here's the formula. If h0 is the initial height and v0 is the initial velocity and g is the acceleration due to gravity near the surface of the Earth, here's the equation. I'm not explaining this equation. I'm just saying here's the answer. This equation can be derived, and we will derive it, from more fundamental principles, Newton's laws, essentially, and the idea of integration will allow us to derive this formula later in the semester. For the moment, you're just trusting me. This is what people use when there's negligible air resistance. When there's actual air resistance, then it gets a bit more complicated. I am implicitly assuming here h is a height, a positive direction when you go upward. Positive value of h upward. Say the ground or the floor is h equals 0, 0 height. If you were to burrow underground, then h would be negative. But we're assuming whatever object you're dropping or throwing is not going to burrow into the ground. The derivative of t equals a is now called the instantaneous velocity instead of speed at that time. And let's figure out what it is in this case. And why do we call it velocity instead of speed? I call it velocity because it's got a direction to it, and it can even be negative. You can have negative velocities where you cannot have negative speeds. Speed is just how fast are you going. Velocity is how fast you're going and in what direction. And if I declare the upward direction to be positive, that means upward going motion is positive velocity, but downward going motion is negative velocity. Let's derive the instantaneous velocity for this function on the board with these pure symbols involved. F of h equals f of t equals negative g over 2. G is a constant. It's 9.8 meters per second in standard units. Also called 9.8 meters per second squared. Plus v sub 0, that's the initial velocity, which can be positive or negative. If you throw it straight up, that's a positive initial velocity. If you throw it straight down, that's a negative initial velocity. If you drop it, that's a 0 initial velocity. Plus h0, initial height. I'm assuming it's not underground, so h0 can't be negative. The derivative of this thing at time t equals a, once again by definition, is this thing. That's the definition of the derivative. Definition of the derivative. I will give my shorthand reasons for this example as we go. And they're similar to the kinds of reasons you can give on a test. On exam 2, I guess I'm pretty much guaranteeing you there'll be a limit calculation on exam 2, and I'm going to want you to give reasons, brief reasons for each equal sign. And this is the instantaneous velocity as well. I'm abbreviating here. That means instantaneous velocity at t equals a. And that is a definition as well, definition of instantaneous velocity. Is it a justified definition is another question. I'm going to give you one more video to watch. Well, compared to, I guess we did back at the beginning of the semester a video. It's going to be a shorter video. It's going to be a 3 blue, 1 brown video that I mentioned first day of class or so. Getting at instantaneous speed and instantaneous velocity and the sort of conundrums that come up when you try to think about it. People had to think about this for a long time to figure out exactly what they were doing. This next step is just substitution into the function. It says substitution. What is the function? It's this. Okay, it's going to get a little messy. but it's worth doing at least once. There we go. That is f of a plus h. Don't forget to subtract f of a. Replace t with just an a. All divided by h. We're hoping that all the terms that do not involve an h at the top cancel. This next step is just going to be algebra, or you could call it simplification. You could probably even call it arithmetic. Expand this all out. A plus h quantity squared, and it's being multiplied by negative g over 2. It's going to give you that. A plus h squared is going to be a squared plus 2ah plus h squared. Multiply every term by negative g over 2, and you should get this. G over 2 canceled with a 2 there. That's why it's just a negative g ah. And we have this stuff plus v0 a plus v0h plus h0. Distribute the minus sign through here, so you got to be careful. Minus and minus is a plus g over 2 a squared. There's a times in there, but I'll get rid of it. Then minus v0a minus h0. So everything that does not involve just a pure h should cancel. h0, by the way, does not involve a pure h. It's h0, not h. So this should cancel, and it does. That. What else does not involve a pure h? This does not involve one, and it cancels with that. And there's one more thing that cancels these two terms. Let me make my cancellation straight up and down this time. Don't let that confuse you. Maybe with a slight slant there. Right? I canceled everything that did not involve a pure h. That's just simplification, algebra, arithmetic, whatever you want to say. Algebra is probably best for the reason because I use the distributive property, for example. I'm not going to fix it. With what's left, this, just those three, I guess. They all involve a factor of h. It can be factored out. Factor out an h out of this one, and you're left with negative g over a, g times a, excuse me. Factor an h out of this one, you're left with negative g over 2 times h for the first one. Factor an h out of this one, you get positive v0. That's just simplification as well, algebra. Now divide out the h's. That is both algebra and the fact that the value of the limit is independent of what happens to this function when h actually equals 0. Algebra and, very importantly, I'm out of room to write that out. I'll say it verbally. You should write it. The value of the limit is independent of what happens to this function when h equals 0. The value of the limit doesn't depend, is another way to say that, doesn't depend on what happens to this function right there when h equals 0. The function of h, think of h as the derivative. Question?
Can you say it again?
The value of this limit is independent or does not depend on what happens to this function where it's undefined, which is h equals 0. just did a little rearranging there as well. Now I can plug in h equals 0 because of continuity. Not of the original difference quotient, not of this thing, not even this simplified version, but of this thing right here. That's a linear function of h, first power. Graph as a function of h is a straight line. It's continuous. You can evaluate the limit by plugging in h equals 0. And if you do and rewrite it a little, well, let's go ahead and write it. It's negative GA plus d0. And that is correct. But now, I'm going to do something a little weird. I'm going to say, well, you know, why did I bother even calling it t equals a? Why don't I just call it t instead of a? Because, no. I could do the exact same calculation with a t instead of an a. Everywhere you see an a. And I get the exact same answer except with a t there instead of an a. And then I'd say, hey, wait a minute. I guess I could now think of t as a variable and let this be a function of t. I can say f prime of t as a function of t is negative gt plus v0. And that would give you the velocity as a function of t. And depending on the value of v0, it could start out even negative in value. If you graph it as a function of t, you'll get a straight line with a negative slope of negative g, negative 9.8 in standard units, plus v0, which would be your vertical intercept. If you start with a positive velocity, if v0 is up there, the graph is going to look like that. What does this mean? It means you threw it straight up, it went up for a little while, where v is positive, and then at this moment in time, it reached its peak before coming back down and having a negative velocity that gets more and more negative, so it goes faster and faster as it travels downward. On the other hand, if you drop it from rest, if v0 is 0, the graph will look like that. You drop it, it starts falling, it's got a negative velocity the whole time that keeps getting faster and faster because it's more and more negative. And if v0 is negative, the graph looks like that. That means your initial condition is negative velocity, you're throwing it straight downward. The velocity starts out negative, it stays negative, it gets more and more negative, it goes faster and faster. Of course, in real life, there is air resistance. Of course, in real life, there's actually a ground, and it will hit the ground, and something bad might happen, or hit somebody's head. Don't drop rocks from the IDS. Okay. Bad idea, okay? You can solve problems based on this. You can figure out, for example, if you throw it straight up, when does it reach its peak? It's going to reach its peak when this is 0. You can solve physics problems. It reaches the peak, assuming v0 is positive, when f prime of t equals 0, solve that equation for t. Set this equal to 0, solve for t, that's going to be equivalent to t equals v0 over g. Now g is a constant, 9.8, but v0 can be different things. So the faster you throw it, the bigger v0 is going upward, the longer it's going to take to reach the peak. That t is going to be larger when v0 is low. The time to reach the peak is proportional to v0. If v0 is very small, you just flick it upwards. Then it doesn't take very long to reach the peak before it falls. You can also answer questions about when it hits the ground again. Set this equal to 0, solve for t with the quadratic formula. In general, is the best thing to use. Lots of different things you can do. Let's check this with Mathematica. Mathematica will be a tool for us to check some things here, as well as do our projects. Here's a quick way to check this derivative on Mathematica. Do a capital D, and square brackets, and inside the square brackets, go ahead and put your function. And you can go ahead and put in here negative g over 2 t squared plus b0 times t plus h0. I'm not making the zeros subscripts here. Then put a comma t. The capital D is telling Mathematica to differentiate, find the derivative of whatever this function is, and this extra comma with the t is emphasizing t is the variable. Again, whether something's constant or variable is all in your head. But if it's in your head, you've got to make sure you tell Mathematica which thing's the variable. Same answer, negative gt plus b0, just like I derived it. Okay, so there's something new in Mathematica. By the way, if you didn't know this, Mathematica is made by Wolfram Research, which also does Wolfram Alpha. Anybody ever heard of Wolfram Alpha? A couple people over there. Wolfram Alpha is an online math engine, so to speak. And you can access Wolfram Alpha through Mathematica just by pressing the equal sign and typing something like this. Derivative of negative g over 2 t squared plus b0 times t plus h0 with respect to t. I hope this works. Wolfram Alpha runs on artificial intelligence, so it tries to interpret what you want. I hope this works. Let's see. Maybe it wants an extra times in there. Oh, it interpreted what I wanted correctly. Same answer. So type an equal sign first, and then type things in words that you think the artificial intelligence could probably interpret correctly, and it should hopefully work. But it may not always work if you type it wrong, okay, if you don't understand what you're looking for. In general, velocity is the derivative of position, not distance traveled. It's a little confusing. Distance traveled and position can be the same thing, but not always. Let's say I talk about back and forth motion here, me walking. Let's say the edge of this desk is position 0. That direction is the positive positions, that direction is negative positions. Positions can be negative. Just like heights can be negative if you allow yourself to go on the ground. If I travel in this direction, that's a positive velocity. If I turn around and travel in this direction, it's a negative velocity. My position can either be negative. The derivative with respect to time t gives the instantaneous velocity at that time, and we write this. V is f prime of t. And we use the definition of the derivative to write it in terms of the limit. We can also write a la Leibniz. In other words, as Leibniz would do. Leibniz lived about the same time as Newton, co-discoverer of calculus. They both basically thought of it approximately at the same time. Newton a little earlier than Leibniz. Leibniz published his work first. And Leibniz's notation is more typical of what we use than Newton's, and his terminology. You could also write it like that. V equals ds dt. That's called the Leibniz notation for the derivative. You can think of it as this limit or that limit. I'm going back to delta t's here because it's for a conceptual point here. I'm not going to really emphasize that conceptual point until Wednesday. Okay, but this is something to know. We're about out of time. Let me just say, I wanted to do some more examples that included examples like 1 over t, 1 over t squared, even e to the t and sine of t. We don't really have the tools to do the derivatives of these things yet. But let me just show you, you can get Mathematica to do them. I will put the slide back up in a second.
Why is it H? Wouldn't that be delta?
Oh, that's a typo. There should be a delta t right here. I forgot to change it. Copy and paste can be dangerous. You forget to change things. I will come back to the slide in a second, but just let's illustrate. You can get Mathematica, for example, find the derivative of sine. It's cosine. Huh, that's weird. But true. When t is in radians. If t is in degrees, that doesn't work. That's why radians is better than degrees. All right.